Hello, my name is Yehu, a PhD student from Washington University in St. Louis. Today I'm going to present our paper, a multitask Gaussian process model for inferring time-variant treatment effects in panel data. This is joint work with Professor Roman Garnett, Professor Jacob Montgomery, and PhD student Anna Maria Prati from Washington University. Let me start with a brief introduction of causal inference. One of the goals of causal inference is to derive the treatment effects of certain intervention. The intervention is usually randomized in randomized control trials, which is considered as the gold standard for causal inference. However, in many social science studies, the interventions are usually some real events and therefore non-randomized. So causal inference with observational study is very common in social science. One of the most common frameworks to study causal inference is called the potential outcome framework. For binary treatment, there is a factual outcome for one treatment status and a counterfactual outcomes for what would have arisen under a different status. The quantity of interest is the average treatment effects untreated, which is the expectation of the two potential outcomes among all the treatment units. The fundamental problem of causal inference is that we can never observe the counterfactual. We can only observe either y1 or y0, but not both of them simultaneously. Therefore, social scientists usually rely on panel data for causal inference. In panel data, outcomes are collected over multiple pre- and post-treatment time periods, so information from pre-treatment observations and controlled observations can be extracted to better estimate the counterfactuals. Such estimation often involves the parallel trend assumption, which assumes that the difference between the treatment and control group is constant over time. So by the parallel trend pre-treatments, we can learn the counterfactual post-treatment. However, the parallel trend assumption may not always hold in reality. For instance, in this figure, the solid treatment trend and Dashman control trends are kind of parallel, but the difference between the trends are definitely increasing over time and by no means constant. This may be caused by heterogeneous time confounding due to unmeasured temporal shocks. In addition, the treatment effects can also be heterogeneous. The effects may depend on subgroups and can also be delayed post-treatment. To account for such heterogeneity and time confounding, many methods rely on the following regression form. The outcomes are decomposed into 5 components: the covariance effect H, the group trend gamma, unit trend U, treatment effects delta, and noise. For the treatment effect to be identified, these models will assume that all confounders are observed and included into the model, and there is no effect pre-treatment. So by correctly learning H, gamma, and U, we can recover delta. However, existing methods all have its own shortcomings for either of the components. Some of the models have no temporal structures. That means the entries in either group and unit trends and the treatment effects are estimated separately rather than jointly. These methods include the standard two-way fixed effect methods, synthetic control method, and the matrix completion methods. Some methods do include temporal structures, but either miss group trends or unit trends. Models like mixed effect GP functional regressions assume that the time trends are the same across every single unit, so no time heterogeneity can be accounted for. On the other hand, some models assume that there is no group trend but only unit trend. They basically have separate time trends for each unit, so any cross-unit similarity is ignored. Finally, some models make too strong or weak assumptions on treatment effects. They either assume rigid parametric models on the evolution of treatment effects, or they simply use completely agnostic models. Accordingly, to include temporal structures in non-parallel trends, we propose MGP panel, a multitask Gaussian process model for panel data. Multitask GP is an extension of single-task GP for modeling joint correlated functions. Multitask GP can be realized using separable kernels, where the covariance function is the connector product of the inputs and task kernel. The novelty of our multitask GP model is its ability to capture non-parallel trends. Rather than being fixed to 1, we can learn the degree of correlation using the off-diagonal value rho in the 2x2 task covariance matrix. By doing fully Bayesian inference for all model parameters including rho, we can further perform Bayesian hypothesis testing for PTA, rather than simply assume it should be true. The other novelty of our model is our regularization prior for delta. We assume that treatment effect smoothly deviates from 0 to some full effect size. This is done by scaling the standard square exponential kernel with the scaling function s. The scaling function is parameterized by a starting point, which indicates the time of intervention, and a peak point, indicating the time of full effect size. So by this additional process, our model can jointly estimate the evolution of treatment effects over all post-treatment periods. To address potential identification issue, we also analyze the asymptotic properties of MGP panel. Our analysis is based on the following reasoning. The post-treatment treated factual is equal to the sum of post-treatment treated counterfactual plus the treatment effects. If we can identify the post-treatment counterfactual at least partially, then we can identify the treatment effects. Based on this reasoning, we derived the joint posterior of post-treatment treated counterfactual and treatment effect. We found out that our model can exactly identify all factual outcomes, especially the post-treatment factual trends. They can be exactly identified in large sample limits, so we are sure we know the sum. We also found that our model can at least partially identify the treatment effects. When we don't have PTA, the uncertainty in the treatment effects is unavoidable but falls asymptotically to some non-zero bounds, decreasing in rho. Moreover, when we have PTA, the uncertainty collapses to 0, so we have exact identification. Now let's talk about some experimental results. We compare our proposed methods to existing baseline such as the two-way fixed effect and the generalized synthetic control, and other Bayesian or Gaussian process methods such as dynamic multi-level latent factor model. The figures shows the root mean square error, the coverage rate, and average log likelihood of our methods against best baseline. We found that MGP panel performs no worse than baselines when PTA holds, and significantly better when PTA is violated. This is because that our model do not rely on the parallel trend assumption, but uses multitask structure to learn non-parallel trends, so we can better estimate the post-treatment counterfactuals. We also perform a ablation study to demonstrate the effectiveness of each component in our model. Some of the ablated model includes no effect trends, no unit trends, linear trends, and strictly parallel trends. We found that no ablated model did significantly better than the full model, and amongst all ablated models, linear trends and parallel trends did worse. This finding provides another piece of evidence that MGP panel succeed due to its ability to capture nonlinear and non-parallel trends. Furthermore, we conducted additional simulations to examine whether our proposed methods is robust to model misspecification. We alter among a variety of data generating processes from heavily tailed non-Gaussian noise, non-smooth trends, observing one unit per group, to completely uncorrelated group trends. We found MGP panel still outperforms the baselines under the majority of these settings, so we conclude that our model is robust under mild to moderate misspecification. However, we are by no means advising practitioners to follow our model strictly, but to suggest that our model can be flexible. For instance, if group trends turn out to be non-smooth, we can use a different kernel other than square exponential kernel or do some model selection before running experiments. Finally, we apply MGP panel to a real-world data studying the local news coverage after acquisition by national company. The data consists of topics of news coverage of 25 television stations over 6 months. The blue shaded area shows our model fit for the factual trends, and the green shaded area shows the estimated counterfactual trends. We found out that acquisition by national broadcasting group increased the proportion of national news coverage in local news stations by around 3% after 2 months, which agrees with the finding in the original study. Equally interesting, we also showed the posterior density of the correlation parameter. We found that the posterior mode is around 0.85 and the 95% confidence interval is from 0.6 to 0.93. This demonstrates that our model indicates higher correlated but non-parallel trends in the data. To conclude, we propose a multitask Gaussian process model for inferring time-variant treatment effects in panel data by using the multitask Gaussian process to learn non-parallel trends. We believe that our model can be adapted for other designs and settings. Our discussion so far is completely based on the block design, where units receive treatment simultaneously. However, staggered adoption is also common in social science, where participants enter the treatment programs at different times. In addition, completely randomization is also possible for treatment reversal, where units may leave and re-enter the program. For these designs, we can adjust the treatment effect kernel in our model to allow wear-off effects by using a different scaling function that scales upwards after intervention but downwards after leave time. We can also model heterogeneous effects, where the effect kernel is further dependent on individual characteristics besides the intervention time. Finally, our task kernel can be adjusted to take different dosage levels so we can handle continuous treatment in applications like dose response learning.